Hey guys, this is Mr. Bennett, and this is Unit 15, video number 1. We're going to talk about solubility. So the first thing we need to talk about is basically what a solution is. A solution is a homogeneous mixture of two or more substances. So we talked about these guys really early in the year, and now we're kind of revisiting this topic. Now, a solution is made up of two parts. First of all, you have the part of the solution that's being dissolved. We call that the solute. And then you have the part of the solution that actually does the dissolving, known as the solvent. And typically, you can know that the solvent, or at least identify the solvent, as the substance that is in greater amount. So whichever of the two substances that you have more of, that's going to be your solvent. Okay, so over here you can see I have a picture here of a glass of water, and we're pouring salt in. So here we have our salt, and here we have our glass of water. So in this particular case here, the salt, which we have less of, is the solute, and the water is the solvent. Now, another way of identifying this would be to look at which one is actually being dissolved, and by dissolved, we mean which one is essentially disappearing into the other substance. Is it really disappearing? No, it's still there, but you're unable to see the salt anymore. And don't get too hung up on that, because sometimes things will dissolve. You can still see that they're there. For instance, Kool-Aid dissolves in water, and you can still see the Kool-Aid's there because you can see the color, but it essentially becomes part of the solvent. It becomes mixed within. I really feel like the easiest way to identify a solvent to solute is that the solvent will be the one that you have the most of. Alright, so it turns out that solutions you can actually be made up of any of the three phases of matter. So solid, liquid, or gas. Now just for some examples, gas dissolved in gas, a good example of that would just be air. So you have, for instance, nitrogen, oxygen, carbon dioxide, different gases that are all homogeneously mixed together. That would be air. Okay, so you can have a solution of air. You can have liquid dissolved in air, something like cloud, which is basically water vapor dissolved in air. Then you could have liquid dissolved in liquid. So this would be something like taking, for instance, some kind of like flavor, or even like a better example would be food coloring, and dropping it into water. And basically the food coloring spreads out and changes the color of your water. Okay. You can also put gas in a liquid. So gas in a liquid, be a good example of that would be something like a carbonated drink. So any type of carbonation is really just carbon dioxide gas that has been dissolved in a liquid. You can dissolve a solid in a liquid, which is basically what we see up here. Salt water is a good example of that. We take solid salt and we dissolve it in the liquid water. And then you can also have solids dissolved in solids. Solid dissolved in a solid, a good example of that would be something we call an alloy, which is really just a metal mixed with a metal. So for example, brass, which is a combination of two different metals. You can also put metal alloys, but it's metal mixed with a metal. Solid mixed with a solid. One thing I did leave off here is you can actually have a liquid in a solid. And so a good example of that would be something like putty or clay, silly putty, things like that, Play-Doh, where you have a solid, but it has that freedom of the ability to change its shape because it has some liquid dissolved in it. Okay, so these are all examples of different solutions. The key thing about a solution is that it's a homogeneous mixture made up of two or more substances, and don't get too hung up on the phases. It can be any of the three phases. Alright, so let's do a little practice real quick. So in terms of identifying these things, what is the solute in chocolate milk? Well, the solute is the thing that's being dissolved, or the thing you have less of, and so typically that's going to be the chocolate. And then what is the solvent in coffee? See if you can get this one on your own while I'm talking. So when we make coffee, right, we take the coffee beans, we put it in the coffee maker. Of course, they're ground first, and then the solvent would be water. And then last but not least, what is the sugar in iced tea? So we make our iced tea, we take a sip, maybe it's not sweet enough, so we add some sugar to it. So is the sugar the solute or the solvent? What do you think? Well, the sugar dissolves into the tea, right? So therefore it would be the solute. Alright, so that's good practice. We'll have more practice on this tomorrow. The second topic I want to talk about in this particular set of notes is what is dissolving actually. So when we say something is dissolving, what is actually happening? Well, it turns out there's actually a word for describing the process of dissolving. We call that solvation. So solvation is the process of dissolving. So when something dissolves, it has solvated. Now, it turns out that you can actually measure how dissolvable a substance is, and we call that solubility. So it is the specific amount of solute that can be dissolved in a specific amount of solvent at a specific temperature and pressure. It turns out that temperature and pressure are actually really important because they will actually alter the solubility. So at different temperatures the solubility can vary a little bit. At different pressures the solubility will vary a little bit. Okay, so let's visualize what that actually looks like. If we look at my picture over here, what we have is basically a beaker of water and we're adding salt to it. So what's really going on at the molecular level? Well, you have these salt crystals, which are a combination of sodium ions and chlorine ions, and they're really just hanging on to each other because of their ionic charges. So the positive is attracted to the negative. Well, it turns out that water, on the other hand, which is basically an oxygen combined to two hydrogens, has a slightly negative end and it has a slightly positive end. Right? These hydrogens carry a slight positive, the oxygen carries a slight negative, and we call this a polar molecule. Well, these charges are attracted to the charges that are in the salt. So as these water molecules get close to the salt crystal, they start attracting those opposite charges, and they'll start pulling them off. So you can see here where a water molecule has separated a negative chlorine. And you can see over here, right here, where a positive sodium has been pulled away by some water molecules. And as time goes on and water molecules collide with our salt crystal, they're going to be attracted to and pull off pieces of this crystal. And you can see that pieces or ions, whether it's chlorine or sodium, you can see right here actually there's a really nice positive sodium that's completely surrounded by water molecules. You can see that here, you can see that here, and here we have a solid or a chlorine ion that has also, or chloride ion, that has also been surrounded by water molecules. So the longer we let this crystal sit in the water and the more contact it has with the water molecules, the more it gets pulled apart, until eventually the crystal is gone and all of these little ions are completely spread out throughout the entire solution. Okay, so this is what's happening. This is the process of solvation. You're taking the crystal and you're slowly breaking it up into the individual ions or pieces. Okay, dispersing it so that it's homogeneous, meaning it's the same throughout the entire solution. Now, how do we affect that solubility? In other words, what controls how soluble a substance is? Well, the first thing that controls solubility is the polarity of the solute and solvent. So in this case over here, we had water, which is a polar molecule, interacting with an ionic molecule. In other words, they both have charges. Okay, it turns out that's really good. The opposite charges can interact, and you can get some really good solubility. If we had something non-polar here that didn't have a charge, neither of these would be able to interact with it, and you wouldn't get any solubility. So the rule of thumb is like dissolves like. So what that means is oil, or actually we would say non-polar, mixes with non-polar, and we would say that polar mixes with polar. But if you try to do the opposite, if you try to mix non-polar with polar, it's not going to work. It won't mix. Okay, so here's an example. If I take oil and water and I try to mix them together, oil is a non-polar substance, Okay, and water is a polar substance. Turns out we would say that this is immiscible. So here's another vocab word. Immiscible means they do not mix. Does not mix. Because they are not like, meaning they don't have the same polarity. Water and salt, on the other hand, is a polar with basically a polar. Ionic and polar you can think of as being the same thing in this case. And so we would say that they are miscible, which is a fancy way of saying they are mixable. Okay, so polarity is a huge factor for affecting solubility. Okay, nonpolar things will not dissolve in polar things, and basically, if you want them to mix, they have to have the same polarity. Okay, so polarity is one factor. The other two factors we've already mentioned. They are temperature and pressure. So if you change the temperature and the pressure, you will affect the solubility. Okay. Now the last thing I want to point out, this is real quick, and you actually know this, or at least should know this, just from like everyday instances, and that is in order to affect the rate of solvation. So in other words, if we have our salt crystal and we want to speed up how fast it dissolves, you can do that by stirring or shaking, right? So like chocolate milk, you put a spoon in there and you stir it up. You can also do it by breaking it up into smaller pieces. So this is what we're doing when we like grind things up. For instance, salt. You don't take a giant chunk of salt and drop it into a glass of water. We take granulated or really fine powdered salt and put that in water because it dissolves faster. So break it up into smaller pieces. And then the last way is you can change the temperature. Again, this is what we do when we want more of something to dissolve. We can heat up, for instance, a liquid, which will allow more solid to dissolve in it. Now the temperature is dependent on the type of mixture. Earlier we talked about air mixing with air mixing with liquid. It turns out the temperature will play a different role here depending on what type of solution you're looking at. But the point is that changing the temperature will affect the rate of dissolving. Okay, so make sure that you complete the whisk, and we'll see you tomorrow.